Lecture 6, Principle of Least Action. Lenny was frustrated, not a good sign considering his size and strength, and his head hurt. George, I can't remember all this stuff. Forces, masses, Newton's equations, momentum, energy. You told me that I didn't need to memorize this stuff to do physics. Can't you make it just one thing to remember? Okay, Lenny, calm down. I'll make it simple. All you have to remember is that action is always stationary. The transition to advanced mechanics. The principle of least action, really the principle of stationary action, is the most compact form of classical laws of physics. This simple rule, it can be written in one single line, summarizes everything. Not only the principles of classical mechanics, but electromagnetism, general relativity, quantum mechanics, everything known about chemistry, right down to the ultimate known constituents of matter, elementary particles. Let's begin with a general observation about the basic problem of classical mechanics. Namely, this problem is to determine the trajectories or orbits of systems from their equations of motion. We usually express the problem by postulating three things: the masses of the particles, a set of forces, F curly bracket x, or even better, a formula for the potential energy, and an initial condition. The system begins with some values of coordinates and velocities and then moves, according to Newton's second law, under the influence of the given forces. If there are a total of n coordinates, x1, x2, x3, till x capital N, then initial conditions consist of specifying the two n positions and velocities. For example, at an initial time t0, we can specify the positions set of x and the velocities set of x dot, and then solve the equations to find out what the positions and velocities will be at a later time t1. In the process, we will usually determine the whole trajectory between t0 and t1. See figure 1. Figure 1, a trajectory from t0 to time t1. But we can formulate the problem of classical mechanics in another way that also involves specifying two n items of information. Instead of providing the initial positions and velocities, we provide the initial and final positions. Here is the way to think about it. Suppose that an outfielder wants to throw a baseball from x0 at time t0 and he wants it to arrive at second base, x1, after exactly 1.5 seconds, t1. How does the ball have to move in between? Part of the problem in this case will be to determine what the initial velocity of the ball has to be. The initial velocity is not part of the input data in this way of posing the question. It is part of the solution. Let's draw a space-time picture to illustrate the point. See figure 2. The horizontal axis shows the position of a particle or the baseball, and the vertical axis denotes the time. The beginning and the end of the trajectory are a pair of points on the space-time diagram, and the trajectory itself is a curve connecting the points. Figure 2, a trajectory of the baseball. The two ways of posing the problem of motion are analogous to two ways of formulating the problem of fixing a straight line in space. One thing we could ask is to construct a straight line from the origin that begins in some particular direction. That's like asking for the trajectory given the initial position and velocity. On the other hand, we could ask to construct a straight line that connects two particular points. That is like finding the trajectory that begins at one position and arrives at another position after a specified time. In this form, the problem is similar to asking how we have to aim a line from some initial point so that it passes through another point. The answer, find the shortest path between the points. In the problems of classical mechanics, the answer is to find the path of a stationary action. Action and the Lagrangian. Formulating the action principle involves exactly the same parameters as formulating Newton's equations. You have to know the masses of the particles and you have to know the potential energy. The action for a trajectory is an integral from the start of the trajectory at t0 to the end of the trajectory at t1. I'll just tell you what the integral is, no motivation, and then we'll explore the consequences of minimizing it. We'll end up with Newton's equations. Once we see how that works, any further motivation will be unnecessary. If it's equivalent to Newton's equations, what more motivation do we need? Before being general, let's illustrate the idea for a single particle moving on a line. The position of the particle at time t is xt and its velocity is xt dot. The kinetic and potential energies are T equals half m x dot square and V equals Vx respectively. The action of a trajectory is written A equals integration from t0 to t1 t minus v dt which when expanded becomes integration from t0 to t1 half m x dot square minus vx dt, equation 1. You might think there is a typo in equation 1. The energy is the sum of t and v, but integral involves the difference. Why the difference and not the sum? You can try the derivation with t plus v, but you will get the wrong answer. The quantity t minus v is called the Lagrangian of the system and is denoted by the symbol L. The things you need to know to specify L are the mass of the particle for the kinetic energy and the potential Vx. It is, of course, no accident that these are the same things you need to know to write Newton's equations of motion. Think of the Lagrangian as a function of the position x and the velocity x dot. It's a function of position because the potential energy depends on x, and it's a function of velocity because the kinetic energy depends on x dot. So we write L equals L as a function of x and x dot. We can rewrite the action as the integral of the Lagrangian. A equals integration from t0 to t1, L x to x dot, L as a function of x and x dot with respect to dt, equation 2. The principle of stationary action is really very remarkable. It almost seems that the particle must have supernatural powers to fill out all the possible trajectories and pick the one that makes the action stationary. Let's pause to consider what we are doing and where we are going. The process of minimizing the action is a generalization of minimizing a function. The action is not an ordinary function of a few variables. It depends on an infinity of variables, all the coordinates at every instant of time. Imagine replacing the continuous trajectory by stroboscopic trajectory consisting of 1,000,000 points. Each point is specified by a coordinate x, but the whole trajectory is specified only when 1,000,000 x's are specified. The action is a function of the whole trajectory, so it is the function of 1,000,000 variables. Minimizing the action involves 1,000,000 equations. Time is not really stroboscopic, and a real trajectory is a function of a continuously infinite number of variables. To put it another way, the trajectory is specified by a function xt, and the action is a function of a function. A function of a function, a quantity that depends on an entire function, is called a functional. Minimizing a functional is the subject of a branch of mathematics called the calculus of variations. Nevertheless, despite the differences from ordinary functions, the conditions for a stationary action strongly resembles the condition for a stationary point of a function. In fact, it has the exactly same form as equation 4 in interlude 3, namely del A equals 0. Now, however, the variations are not just small shifts of a few coordinates, but all the possible small variations of a whole trajectory. Later in this lecture, we will work out the equations for minimizing the action. They are called the Euler-Lagrange equations. For the case of a single degree of freedom, there is one equation at each point along the trajectory. In fact, the equations become differential equations that tell the system how to move from one instant to the next. Thus, the particle does not have to have supernatural powers to test out all future trajectories, at least no more so than it needs to follow Newton's equations of motion. We will derive the Euler-Lagrange equations later in this lecture. To do you a favor, I will write down their form. If you are the independent type, you can try to plug in the Lagrangian and see if you can derive Newton's equations of motion. Here, then, is the Euler-Lagrange equation for a single degree of freedom. The time derivative of the partial derivative of Lagrange with respect to x minus the partial derivative of Lagrange with respect to x equals 0. Derivation of the Euler-Lagrange equation. Let's see if we can derive the Euler-Lagrange equation for a single degree of freedom. Start by replacing continuous time with stroboscopic time. The instants can be leveled by integers n. The time between neighboring instants is very small. Call it delta t. The action is an integral, but as always, an integral is the limit of a sum. In this case, we are going to think of the sum as being over the intervals between successive instants. Here are the replacements that we do when we approximate the integral by the sum. Integration of L with respect to dt equals the summation of L times delta t. And x dot equals x at n plus 1 minus x at n divided by delta t. The first replacement is just the usual approximation of replacing the integral by a discrete sum of terms, each weighted with the small time interval delta t. The second is also familiar. It replaces the velocity x dot with the difference of neighboring positions divided by the small time interval. The last replacement is a bit more subtle, since we are going to think of this sum as being over the small intervals between neighboring instants. We need an expression for the position halfway between the instants. That's easy. Just replace xt with the average position between the neighboring instants. xt equals xn plus 1 by 2. Notice that everywhere x dot occurred in the Lagrangian one replaced it with x at n plus 1 minus x at n by delta t, and everywhere that x occurred I substituted x at n plus x at n plus 1 by 2. The total action is found by adding up all the incremental contributions. That means A equals summation n, L, a function of xn plus 1 minus xn by delta t, and xn plus 1 by 2 times delta t. This is equation 3. I have very explicitly taken the action apart into its components, almost like writing a computer program to evaluate it. Now suppose we want to minimize the action by varying any one of the xn and setting the result equal to 0. Let's pick one of them, say x8. Any other one would have been just as good. This sounds very complicated, but notice that x8 appears only in two of the terms in equation 3. The two terms that contain x8 are A equals L as a function of x9 minus x8 by delta t, comma x8 plus x9 by 2 whole delta t plus Lagrange x8 minus xn by delta t, comma x7 plus x8 by delta by 2 whole times delta t. Now all we have to do is differentiate with respect to x8. Notice that x8 appears in two ways in each term. It appears through the velocity dependence and through the x dependence. The derivative of a with respect to x8 is the partial derivative of a with respect to dx8 equals 1 by delta t inside bracket minus partial derivative of Lagrange with respect to x at n is equal to 9 plus partial derivative of Lagrange with respect to dx dot at n is equal to 8 plus half partial derivative of Lagrange with respect to x at n is equal to 8 plus partial derivative of L with respect to x at n is equal to 9. The symbol line n is equal to 8 is an instruction to evaluate the function at the discrete time n equals 8. To minimize the action with respect to variations of x8, we set dA by dx equals 0. But before we do, let's see what happens to dA by dx in the limit when delta t tends to 0. You start with the first term. 1 by delta t bracket minus partial derivative of Lagrange with respect to dx dot at n equals 9 plus partial derivative of Lagrange with respect to dx dot at n equals 8. This has the form of the difference between a quantity evaluated at two neighboring times, n is equal to 8 and n equals 9, divided by the small separation between them. This obviously tends to a derivative, namely minus d by dt del L by del x dot. The second term, half dl by dx n is equal to 8 and partial derivative L by x at n is equal to 9, also has a simple limit. It is the half the sum of dl by dx evaluated at neighboring times. As the separation between the points shrinks to 0, we just get the partial derivative of the Lagrange with respect to x. The condition that dA by dx8 equals 0 becomes the Euler-Lagrange equation d by dt of dl by dx dot minus dl by dx, the partial derivative, equals 0, which is the equation 4. Exercise 1. Show that equation 4 is just another form of Newton's equation of the motion F equals ma. The derivation is essentially the same for many degrees of freedom. There is an Euler-Lagrange equation for each coordinate xi. That is the time derivative of the partial derivative of Lagrange with respect to x dot I minus the partial derivative of Lagrange with respect to x dot I equals 0. What this derivation shows is that there is no magic involved in the ability of the particle to fill out the entire path before deciding which way to go. At each stage along the trajectory, the particle has only to minimize the action between a point in time and the neighboring point in time. The principle of least action just becomes a differential equation at each instant that determines the immediate future. More particles, more dimensions. Altogether, let there be n coordinates that we call xi. The motion of the system is described by a trajectory or orbit through an n-dimensional space. For an even better description, we can add time, thinking of the orbit as a path through n plus 1 dimensions. The starting point of the trajectory is the set of points xi at t naught, and the endpoint is another set of points at xi at t1. The orbit through the n+1 dimensional space is described by giving all the coordinates as functions of time xi at t. The principle of least action for more degrees of freedom is essentially no different than the case with only a single degree of freedom. The Lagrangian is the kinetic energy minus the potential energy. L equals summation I half mi xi dot square minus v curly bracket x. The action is also exactly as before, the integral of the Lagrangian. A equals the integration from t0 to t1, Lagrangian as a function of set x and set x dot integrated with respect to dt. This is equation 5. And the principle of least action, stationary action, is that the trajectory minimizes the action. When there are many variables, we can vary the trajectory in many ways. For example, we can vary x1t or x2t and so on. It's like minimizing a function of many variables. There is an equation for each variable. The same is true for the Euler-Lagrange equations. There is one variable xi. Each one has the same general form as equation 4. The time derivative of the partial derivative of Lagrange with respect to xi dot equals the partial derivative of Lagrange with respect to xi. And this is the equation 6. Exercise 2. Show that equation 6 is just another form of Newton's equation of motion Fi equals mi xi double dot. What's good about least action? There are two primary reasons for using principle of least action. First, it packages everything about a system in a very concise way. All the parameters, such as the masses and forces, and all the equations of motion are packaged in a single function, the Lagrangian. Once you know the Lagrangian, the only thing left to specify is the initial conditions. That's really an advance, a single function summarizing the behavior of any number of degrees of freedom. In future volumes, we will find that whole theories, Maxwell's theory of electrodynamics, Einstein's theory of gravity, the standard model of elementary particles, are each described by a Lagrangian. The second reason for using the principle of least action is the practical advantage of the Lagrangian formulation of mechanics. We'll illustrate it by an example. Suppose we want to write Newton's equations in some other coordinates, or in some frame of reference that is moving or accelerating. Take the case of a particle in one dimension that, from the point of view of someone standing at rest, satisfies Newton's laws. The physicist at rest, call him Lenny, uses the coordinate x to locate the object. A second physicist, George, is moving relative to Lenny, and he wants to know how to describe the object relative to his own coordinates. First of all, what does it mean to talk about George's coordinates? Because George moves relative to Lenny, the origin of his coordinate frame moves relative to Lenny's origin. This is easily described by changing coordinates from Lenny's x to George's coordinate system, capital X. Here is how we do it. At any time t, Lenny locates George's origin at x plus ft, where f is some function that describes how George moves relative to Lenny at event at time t. Then Lenny assigns a coordinate x. George assigns coordinate capital X, where capital X equals x minus ft. When Lenny sees a particle moving on the trajectory xt, George sees the same particle moving on the trajectory capital X equals xt minus ft. If George does not want to keep asking Lenny what the trajectory is, then he wants his own laws of motion to describe the object from his coordinates. The easiest way to do this is to transform the equations of motion from one coordinate system to another, is to use the principle of least action, or the Euler-Lagrange equations. According to Lenny, the action of a trajectory is A equals the integration from t0 to t1 inside brackets half m x dot square minus potential function vx with respect to dt. This is equation 7. But we can also write the action in terms of George's coordinates. All we have to do is to express x dot in terms of capital X dot. Small x dot equals capital X dot plus f dot. So we plug this into equation 7 to get A equals the integration from t0 to t1 half m under brackets capital X dot plus f dot whole square minus potential function v as a variable of capital X dt. The potential energy capital V, capital X simply means the potential energy that Lenny would use evaluated at the object's location but expressed in George's coordinates, same point, different level. And now we know the Lagrangian in the X frame of reference. Capital L equals half m x dot plus f dot whole square minus potential function as a function of capital X. Where we can expand the square, L equal to half m x dot square plus 2x dot f dot plus f dot square minus potential function Vx. This is equation 8. What does George do with equation 8? He writes the Euler-Lagrange equation. Here is what he gets. mx double dot plus mf double dot equals to minus the derivative of v with respect to capital X. Or with a small rearrangement, f mx double dot minus dv by dx is equal to minus mf double dot. The result is nothing surprising. George sees an extra fictitious force on the object equal to minus mf double dot. What is interesting is the procedure. Instead of transforming the equation of motion, we work directly with the Lagrangian. Let's do another example. This time George is on a rotating carousel. Lenny's coordinates are x and y. George's coordinate frame is capital X and capital Y, and it rotates with the carousel. Here is the connection between the two frames. Small x equals capital X cos omega t plus y sin omega t. Small y is equal to minus x sin omega t plus y cos omega t. This is equation 9. Both observers see a particle moving in the plane. Let's assume that Lenny observes that the particle moves with no forces acting on it. He describes the motion using the action principle with Lagrangian. Capital L equals m by 2 under brackets x dot square plus y dot square, and this is the equation 10. What we want to do is express the action in George's rotating frame and then use the Euler-Lagrange equations to figure out the equations of motion. Since we already know the action in Lenny's frame, all we need to do is express the velocity in his frame of reference in terms of George's variables. Just differentiate equations 9 with respect to time. As seen here, x dot cos omega t minus w x sin omega t plus y dot sin omega t plus w y cos omega t, and similarly small y dot becomes minus x dot sin omega t minus omega x cos omega t plus y dot cos omega t minus omega y sin omega t. After a little bit of algebra using sin square plus cos square equals 1, here is what we get for x dot square plus y dot square. That eventually becomes x dot square capital plus y dot square plus omega square inside bracket x square plus y square plus 2 omega x dot y minus y dot x, which is equation 11. Now all we have to do is plug equation 11 into Lenny's Lagrangian, equation 10, to get George's Lagrangian. It's the same Lagrangian except expressed in George's coordinates, as shown in equation 12. Let's examine the various terms. The first term, m by 2 capital X dot square plus y dot square, is familiar. It's just what George would call the kinetic energy. Notice that if angular velocity were 0, that's all there would be. The next term, m omega square plus x square plus y square, is something new due to the rotation. What it looks like to George is a potential energy. Potential equals to minus m omega square inside bracket x square plus y square, which can easily be seen to create an outward force proportional to the distance from the center of rotation. Force equals m omega square, the position vector r. This is nothing but the centrifugal force. The last term in equation 12 is a little less familiar. It is called the Coriolis force. To see how it all works, we can work out the Euler-Lagrange equations. Here is what we get. As shown in the figure, mass m times capital X double dot equals m omega square x minus 2m omega y dot, and my double dot equals m omega square y plus 2m omega x dot. This looks exactly like Newton's equations with centrifugal and Coriolis forces. Notice that there is something new in the form of the force law, the components of the Coriolis force. Therefore, fx equals minus 2m omega y dot and fy equals 2m omega x dot. Depend not only on the position of the particle but also on its velocity. The Coriolis force is a velocity-dependent force. Exercise 3. Use the Euler-Lagrange equations to derive the equations of motion from this Lagrangian. The main point of this exercise was not so much to derive the centrifugal and Coriolis forces as to show how you transform a mechanics problem from one coordinate system to another by simply rewriting the Lagrangian in the new coordinates. This is by far the easiest way to do the transformation, a lot easier than trying to transform Newton's equations directly. Another example, which we will leave to you, is to transform George's equation to polar coordinates. Capital X is equal to r cos theta and capital Y is equal to r sin theta. Exercise 4. Work out George's Lagrangian and Euler-Lagrange equations in polar coordinates. Generalized coordinates and momenta. There is really nothing very general about Cartesian coordinates. There are many coordinate systems that we can choose to represent any mechanical system. For example, suppose we want to study the motion of an object moving on a spherical surface, say the Earth's surface. In this case, Cartesian coordinates are not of much use. The natural coordinates are two angles, longitude and latitude. Even more general would be an object rolling on a general curved surface like a hilly terrain. In such a case, there may not be any special set of coordinates. That's why it is important to set up the equations of classical mechanics in a general way that applies to any coordinate system. Consider an abstract problem in which a system is specified by a general set of coordinates. We usually reserve the notation xi for Cartesian coordinates. The notation for general system of coordinates is called qi. The qi could be Cartesian coordinates or polar coordinates or anything else we can think of. We also need to specify the velocities, which in the general abstract situation means the time derivatives of the qi generalized coordinates. An initial condition consists of the set of generalized coordinates and the velocities, set qi, qi dot. In a general coordinate system, the equations of the motion may be complicated, but the action principle always applies. All systems of classical physics, even waves and fields, are described by a Lagrangian. Sometimes the Lagrangian is calculated from some previous knowledge. An example is calculating George's Lagrangian, knowing Lenny's. Sometimes the Lagrangian is guessed on the basis of some theoretical prejudices or principles, and sometimes we deduce it from experiments. But however we get it, the Lagrangian neatly summarizes all the equations of motion in a simple package. Why are all systems described by action principles and Lagrangians? It's not easy to say, but the reason is very closely related to the quantum origins of classical physics. It is also closely related to the conservation of energy. For now, we are going to take it as a given that all known systems of classical physics can be described in terms of the action principle. The Lagrangian is always a function of the coordinates and velocities. L is equal to L, qi dot, and the action principle is always del A equals del times integration from t0 to t1, Lagrangian as a function of qi and qi dot with respect to dt equals 0. This means that the equations are of the Euler-Lagrange form. Here, then, is the most general of the classical equations of motion. There is an equation of each qi, where time derivative d by dt of partial derivative of dl with respect to dqi equal to dl by dqi dot, partial derivative L with respect to dqi. Equation number 13. That's it. All of the classical physics in a nutshell. If you know what qi's are, and if you know the Lagrangian, then you have it all. Let's look a little closer at two sides of equation 13. Begin with the expression the partial derivative of L with respect to qi dot. Suppose for a moment that qi's are the ordinary Cartesian coordinates of a particle and L is the usual kinetic energy minus potential energy. In this case, the Lagrangian would contain m by 2 x dot square and dl by tqi dot would just be mx dot, in other words, the component of the momentum in the x direction. We then call the partial derivative of L with respect to qi dot the generalized momentum conjugate to qi, or the conjugate momentum to qi. The concept of conjugate momentum transcends the simple example in which the momentum comes out to be mass times velocity. Depending on the Lagrangian, the conjugate momentum may not be anything you recognize, but it is always defined by pi equals the partial derivative of L with respect to qi dot. The notation for generalized momentum is pi. With that definition, the Euler-Lagrange equations are dpi by dt equals the partial derivative of L with respect to qi. Let's do a couple of examples starting with a particle in polar coordinates. In this case, the qi's are the radius r and the angle theta. We can use the result from exercise 4 to get the Lagrangian L equals m by 2 r dot square plus r square times theta square. The generalized momentum conjugate to r, the r momentum, is PR is equal to the partial derivative of r with respect to r dot, also written as mr dot. The corresponding equation of motion is dpr by dt equals dl by dr. That gives us mr theta dot square. Using p dot equals mr double dot and cancelling mass from both sides, we can write this equation in the form r double dot equals r theta dot squared. The equation of motion for angle theta is especially interesting. First, consider the conjugate momentum to theta. P theta equals the partial derivative of L with respect to theta dot equals mr square theta dot. This quantity should be familiar. It is the angular momentum of the particle. Angular momentum and p theta are exactly the same thing. Now consider the equation of motion for theta. Since theta itself does not appear in the Lagrangian, there is no right hand side, and we have dp theta by dt equals 0, which is equation 14. In other words, angular momentum is conserved. Another way to write equation 14 is d by dt of mr square theta dot equals 0, which is equation 15. We can see that r square theta dot is a constant. That's why the angular velocity increases as a particle gets closer to the origin. Exercise 5. Use these results to predict the motion of a pendulum of length L. Cyclic coordinates. As we have just seen, it sometimes happens that some coordinate does not appear in the Lagrangian, though its velocity does. Such coordinates are called cyclic. I don't know why. What we do know is that the Lagrangian does not change when you shift the value of a cyclic coordinate. Whenever a coordinate is cyclic, its conjugate momentum is conserved. Angular momentum is one example. Another is ordinary linear momentum. Take the case of a single particle with Lagrangian. L equals m by 2 in brackets x dot square plus y dot square plus z dot square. None of the coordinates appear in the Lagrangian, so they are all cyclic. Again, there is nothing particularly cyclic about them, it's just a word. Therefore, all of the components of momentum are conserved. This would not be true if there were a potential energy that depended on the coordinates. Let's take another case. Two particles moving on a line with a potential energy that depends on the distance between them. For simplicity, I'll take the masses to be equal, but there is nothing special about that case. Let's call the positions of the particles x1 and x2. The Lagrangian is L equals m by 2 in brackets x1 dot square plus x2 dot square minus v x1 minus x2, equation 16. Now the Lagrangian depends on the both x1 and x2, and neither is cyclic. Neither momentum is conserved. But that's missing an important point. Let's make a change of coordinates. Define x plus and x minus as x plus equals x1 plus x2 by 2 and x minus equals x1 minus x2 by 2. We can easily rewrite the Lagrangian. The kinetic energy equals T equals m x plus dot square plus x minus dot square. Exercise 6. Explain how we derived this. The important point is that the potential energy depends only on x minus. The Lagrangian is then L equals m in brackets x plus dot square plus x minus dot square minus v x minus. In other words, there was a hidden cyclic coordinate, namely x plus. This means that the conjugate momentum to x plus, call it p plus, is conserved. It is easy to see that p plus is nothing but the total momentum. P plus equals 2mx plus dot equals mx1 dot plus mx2 dot. The real point that we will come to in the next lecture is not so much about cyclic coordinates but about symmetries.